Hello friends, welcome you to all to the session 15 of ARM-based development. So in this class we will be covering basically aborts and two special instructions, SWI, that is software interrupt, and undefined instruction, that is the instruction which is not understandable by the processor. So what is the reaction to that by the processor? So basically these are all part of the exception cases. So this is little involved. I want you guys to pay closer attention to what I am saying today. So we'll touch upon aborts in general, what we mean by aborts, okay, and then prefetch abort and data abort. So by now you should know what these two aborts correspond to when they are generated, but still in this class we will cover the background of this and when these things happen, and in response to these aborts what does the processor do. Then we will talk about the special instruction called SWI, which you might have seen in the simulator code where you might be using one of few of them. There are a whole lot of library functions provided with the simulator using this instruction with a specific parameter. So once you understand how to use it, maybe you can try out all the library functions that are provided with the simulator. But this class is not about how to use them, it is only about understanding what is a software interrupt, okay, and then when does the undefined instruction exception happen in a processor, okay. So this is going to be our focus for today. Okay, let us see what do we mean by abort. An abort indicates that the current memory access, either code or data, cannot be completed. So let me give you the background what we mean by a memory access that cannot be completed. So this is the processor, okay. So it is connected to the memory. Now you know that processor reads both code and data from the memory. Now what are the possible reasons why any of these access, either code access or a data access, cannot be completed, okay. So first of all, let us understand when does the code access happen. Code access happens during the prefetch stage. You know that in a pipeline already the instructions are prefetched, right, 2 instructions down the line. So if there are some instructions, okay, 1, 2, 3 different instructions will be in a different stages of the pipeline. So once this goes out, then this moves in, and then the next instruction 4 gets prefetched here, right. So code gets accessed only during the prefetch. Please understand that during the prefetch only code gets accessed. That means all the code is getting fetched ahead of their execution, okay. So at least 2 cycles before it gets executed, the code is fetched. Now I'll give you an example where a prefetch abort could happen, okay. For this I need to give you some physical memory, virtual memory, but just understand that these things will be covered later, but only for you to understand the background on how these aborts could happen. I am giving you this. So basically you might have heard about virtual address and physical address, okay. So what I mean by physical address and virtual address? Virtual address is something which the programmer thinks, the program thinks that it has got access to a whole lot of big memory, okay. Let us assume a typical ARM processor can 32-bit wide, so it can have larger memory. Assume physically there is a limitation on how much memory you can have it in your system. Okay, this is a processor and memory. This is your embedded system. Okay, assume that you have kept a RAM. Okay, you have put a RAM of maybe say 256 MB. Okay, just an example. You only have a 256 megabytes of RAM. Okay, that means this is a typical example where you have RAM memory and then maybe a flash. Okay, where your code is kept. Okay, so any code or the data that needs to be accessed by a program has to be in the RAM. Okay, RAM. So maybe this whole memory area is divided into some spaces, and code, data, stack, everything is there in this RAM. Now whatever is required, the code, okay, it's not the whole code is brought from flash or a hard disk. It could be a hard disk also in a typical this system with huge memory. But let us, for a embedded system perspective, let us assume that there is a flash, and we can't run the code from flash for some reason because the access time of flash is slower. So always code is also brought into RAM and then executed. So we are talking about that scenario where we have limited RAM memory, and then assume that this is enough for this processor. It need not be ARM, it could be anything. Okay, but what happens is there will be an MMU also could be there. It is a memory management unit. So when you write a program, you may assume that I have a whole lot of maybe 100 MB of memory is there. Okay, you declare that kind of a huge array of data. Okay, or you have a big code which needs to be executed, and they are all placed in 100 MB space. So this is what the program thinks, that it has got a space of 100 MB, but physically there is only, I'm sorry, maybe I mixed up the numbers here. Let me reduce this to 64 MB to convince that this memory is lower than this. So 100 MB of a code and data is there, and then you have only 64 MB of actual physical memory. So this, what the programmer thinks as a virtual memory is 100. Okay, and what physically is there is 64 MB. Okay, at least a balance of this memory is not available. So the whole code and data cannot be brought into the physical memory because of this limitation. Okay, so but you may wonder, how can I run a program which needs 100 MB but with a limited memory space? It is possible because when you are running a code or when you are accessing a data, you are not going to be accessing the whole thing in the same time, right? When a particular piece of code is run, it may access a particular part of the data, and then when it goes to some other part of the code, maybe it may access some other part of the data. So basically what happens is, the MMU, the memory management unit, and then virtual management system, okay, brings in the memory which is needed for the execution to happen, both in terms of data and code. Okay, both in terms of the code and data, it brings what is required, and then it executes them. And then if suppose that code goes to some other part of the code space, then that code, part of the code which is there in the flash, is brought in, and this is not written back because code anyway you are not going to be modifying it. But if suppose the data is there, it will be written back, the old modified data, new data will be brought in. So what I am trying to say is, during using the virtual memory management, okay, and using a separate hardware apart from processor and memory, the typical 100 MB space is mapped to 64 physical memory at different point in time. Okay, so some part of the memory is brought back, and then you execute it and then take it back. So you might have heard about pages or segment. Okay, so assume that you have a page. Okay, this page is currently there, page 1, and you are accessing the code. The program is accessing the code from here, and when the code goes out of this page region, what happens is, yep, code prefetch abort is generated. The memory controller gives the processor saying that, hey, this particular memory what you are looking for is not currently with me in the physical memory. So what happens? Then the OS, if it is running, then it comes into play, and then that particular page which is there in the hard disk or a flash is brought back into the memory, and then the control is given back to the processor to execute the same instruction again. So basically what happens is, a physical memory, limited physical memory helps you in a bigger memory. It will give a feeling that the processor or the program thinks that this whole memory is available to you, but because it is needed, because of locality of reference, it is needed only only during the time of execution. The relevant pages of that is brought back. It could be, the page could be a code or a data, and then executed from the memory. So this is the RAM. Okay, this could be some other secondary memory, it could be disk or some flash which is slower memory, and this is a faster memory. Okay, so this is called virtual memory, and this is called it is done by MMU. Okay, we will be programming MMU how to convert this virtual addresses that program gives into a physical address which is in the memory. Now, why am I explaining this? We will be explaining this later on also, but what I am saying is, when a particular piece of code is not available in the memory, or a data, okay, is not available in the memory, that actually goes back, the memory controller goes back and brings that new page, and by replacing this old page into the memory, back into secondary memory, and then the execution starts. So when this kind of thing happen, the memory management unit or memory controller, which knows both of them working together, will know that there is a problem in the accessing of memory. So it gives an abort signal to the processor, and in turn the processor executes a data abort or a prefetch abort, and the abort handler, okay, the abort handler takes care of this swapping the memory and bringing back the new memory. Okay, this handler could be a part of OS code. Okay, so this is what happens during a typical abort situation. Okay, so the memory access is not possible to be completed. So what happens is that particular problem is fixed, and then the same instruction is executed again. Okay, whichever caused the memory abort, the data abort, that instruction is again executed by fixing the problem. That means what? The page is brought into the memory and then this is executed again. Hope this is clear to you. Okay. So abort is signaled through the external abort input, okay, by the memory controller. Okay, and then ARM processor checks for the abort exception. So how? So a processor is executing the instruction in a sequence. So it has to look for whether abort is there or not. There should be sampled at particular time. So that is happening when M clock is there at the end of every execution. Okay, every memory cycle, not even execution of instruction, even every memory cycle. Because why I am saying it is different from the execution cycle, because suppose if you have a LDM or a STM, that means multiple data is accessed. Okay, there will be multiple memory cycles. Okay, so suppose 16 words have to be accessed. Okay, assume 16 words are to be accessed from memory and then loaded into a register. Okay, using LDM instruction, LDM FD or IA, whatever. Now assume that this is the cutoff where this much memory, this much data is available in the RAM. Okay, assume there is a page is ending here, one page is ending here, page boundary, and new page is starting here. That is possible. Okay, this part of the memory which is needed later on in this, after this cycle, is part of another page, whereas this particular part of it is another page. Now what happens when register 1 0, suppose you are loading 1 2 3 4 5 registers, you are copy values you are copying from memory into a register. So first two registers are copied from the memory, whereas the remaining things to be copied from memory which is not available in the RAM. So it has to be, page fault happens and then it has to be fixed. So even during a part of the execution, the fault can happen. The abort can happen during the middle of a instruction execution. So that is why I am saying that on every cycle, every memory cycle, this may be a non-sequential access and the rest of it will be a sequential access. But after this sequential access, there will be a memory fault and then another non-sequential access happens and continues. So the processor can be interrupted during every, it could happen on any cycle, any part of the memory cycle. So That is why the processor checks for abort on every memory access cycle. So abort mechanism allows the implementation of a demand page retrieve memory. What I mean by demand page, when a particular page is required, that page is brought from secondary memory to the RAM. Okay, that is what is called demand. On demand, you get the page. That is called demand paging, which is a part of OS concept which you might have studied in your previous courses. So I'm just giving you a background on when an abort could happen. Okay, now let us concentrate on prefetch abort. So a prefetch abort is something to do with a code. So when a prefetch abort occurs, code marks the prefetched instruction as invalid. Now I need to give you another example. Okay, this is prefetch is happening here. Okay, prefetch, and then decode happens and execution happens. So assume that these are all a set of instructions, and this instruction is being executed. This is in decode stage and this is in fetch stage. So this particular code is on a page boundary. It could happen, right? Or okay, this is one reason where you are not able to get the instruction because let us assume that it's on the page boundary. Okay, so what happens is this memory is not in the RAM. This code is from this onward, the code is going to a different page and which is not available in the RAM. That is one possibility. Okay, another one is suppose the CPU is here and the memory is there. Okay, assume that there is no memory management unit or anything. This is the starting at a 0 and this is a some address up to maybe 7F. The code is there. Okay, ROM is there, code ROM. So you know very well that beyond this 7FF there is no memory at all in the system. Okay, there is a directly mapped memory. There is no memory management unit or something. Okay, CPU is accessing the memory, and there is a physical limit of 7FF is the maximum value. Now you as a programmer you might know that there is a limit in the memory, and you would have written a code such a way that this beyond this the execution don't go. So suppose let me give you an example where you have written a code at there's some assembler, something is generated, and then you have put a branch to something address, and then the code is ending here. It is not going to go further down. Okay, there is a branch to something above. The code could be placed inside the memory itself. So when this execution is executed, instruction is executed, it is anyway going to jump to some other address. Okay, it could be a higher address. Here I am saying that it's a higher address. So suppose if there is a branch which points to a lower address. Okay, let us avoid this. So there is the code is memory is increasing like this, and there is a branch, and then the code comes back, control goes back. So there is no code beyond this address at all. Okay, but prefetch could, when this is before being executed, it is going to access this, try to access this part of the memory which is not there physically. So memory controller may give an abort, but it may not be a valid abort. So that is why when it is accessing a code, because it is going ahead and accessing the instructions ahead of actual execution, the processor just notes it, make a note of that there was a problem when I tried to access this instruction. Okay, and that information is passed between two stages. Okay, through a pipeline registers. You might remember the pipeline registers that are there to pass on information from one stage to the other. So if this instruction which caused the prefetch abort comes to the execute stage, then only it indicates that it is a valid instruction which was to be executed, but it is not available in the memory. Then it needs a support of OS to handle that abort. So it is not necessary to create an abort on prefetch itself, because there is a possibility that the previous instruction branches and then these two instructions are never executed at all. So to cater for that kind of a condition, it is not executed. The prefetch abort is not executed until it comes to a execute stage. So, but it does not take the exception until the instruction reaches the execute stage. Please understand, this is the reason why an instruction abort happens during a prefetch, but it gets served during the execute. Okay, it will be noted, and then if it reaches the execute state, then abort will be, as soon as it enters, there is nothing to execute, so it will go to the abort signal. Prefetch abort happens. So this is the sequence. Okay, it is noticed here. No action taken in decode stage. When it reaches the execute stage, action is taken. So what action? To bring the page back into the memory or something, so that this same instruction can be fetched again with the after the correction is done. So now the instruction is available in the RAM, so it can be executed. So this is what happens during the abort. Okay, hope you understand this. If the instruction is not executed because the branch occurs while it is in the pipeline, the abort does not take place. Suppose if there is no need for executing that instruction, there is no need to abort. So after dealing with the reason for the abort, the handler executes the following. Okay, now assume that suppose branch is not happened and that instruction has reached the execute stage, then the abort handler will be called. You know that there is a fixed location in the vector table for an instruction prefetch abort. So that vector table it goes, then PC will be it will give a branch to the handler. Handler takes care of doing some correction on the which caused the page fault or the particular cause of the error, and then the control is coming back to the same instruction. Please remember, prefetch happened when two instruction above was being executed, and suppose this is the address 104. During this time, the processor encountered a prefetch abort, and then when it enters the execute stage, it goes to the control goes to the vector table, and then the handler is called, and then suppose some correction has happened. Now again the PC has to be loaded with the same value 104. Okay, which originally caused the abort, so that the same instruction can be now fetched from the memory and executed. Okay, that is the reason why it is coming back to the same instruction. Now I am saying that this is what is done. Okay, let us understand this instruction first. What I mean by that is, in the handler, after fixing the problem of the prefetch abort, the last instruction that is executed in the handler is this. Okay, if you recall, I have explained in the previous section. Okay, when the abort happens, what all is done? Let us go back and recap all those things so that you understand this instruction pretty well. So prefetch happened, okay, at 104, okay, and it entered the execute stage. Now it shows that it has to be executed. That the particular prefetch abort has to be executed. So processor, what does it do? It has to go to the abort mode. Okay, it has to change the abort mode. You go to the abort mode. Suppose you assume that it is in user mode. So user mode has its own registers, and abort mode has got its own register. Abort. Okay. So abort mode has what are the registers? R13, okay, and R14, okay, and then S saved program status register. Okay, I am just recapping on what I providing a recap on what I was explaining last class. So abort happens, it goes to the vector table, okay, go and then gets the address to the abort handler. So abort is executed. Now prior to that, what needs to be done? The instruction which caused has to be actually saved. Okay, but what is saved is, because I told you that prefetch is not handled immediately, it goes to when it comes to execute stage only it is handled. So that time what happens is, the instruction when it enters the prefetch abort execute stage, the PC will be pointing at, this is the instruction 104, okay, it will be pointing at 108 actually, okay. It is trying to access the next instruction. PC would have been incremented, okay, plus 4. So it will be accessing 108. Now that time what happens? The abort is handled. So the PC, whatever the PC value is stored into the link register of abort mode. PC is stored here. That is 108 is stored here. Okay. And then SPSR is loaded with the user mode register is there, right? User mode register, these are all user mode registers. It has got a CPSR, right? So CPSR holds the status of the processor, including the user mode. So that gets CPSR gets saved here, okay, in the SPSR of the abort mode, and then CPSR is modified. The mode bit is changed to abort mode, okay. Abort, it is mode bits are changed. The LSB 5 bits are changed, and then it executes the handler. Okay. Now the execution has come to the end of the handler. Now the control has to come back to the instruction which caused the abort, that is 104. What is stored is in the abort mode register R14, what is stored is 108. So this instruction, so I have shown it as abort here, but actually when you write a code you will not be mentioning underscore ABT, you will be executing R14. So what does it mean? R14 means it is in the abort mode, so R14 of abort mode register, bank register is used. So it is actually storing the CPU has already put the PC value which is next to the instruction which caused the abort into the R14 register. Okay. So that value has to be taken and subtracted by 4. Why do you have to subtract it by 4? Because you are interested in coming back. The CPU is processor has to execute the 104 actually, not 108, because then it will skip this instruction, because while accessing this instruction only it caused an abort. So now this the abort handler has fixed the problem, so that instruction is in the memory, so it has to execute that instruction before going to the next instruction, right? So how will it execute? Only when you give the control back to the same instruction. So PC has to be loaded with the 4 values, 4 by minus 4 has to be loaded, so that PC comes back to the same instruction and executes it. So that can be done only when the R14 is taken from the abort mode, because the processor has already saved that return value, and it is subtracted by 4 and then loaded into PC. Now when you have yes, this I have explained earlier. When you are doing a PC as a destination register, and when S bit is set, okay, this is a very special case where PC is a destination register and S, it doesn't matter whether sub is done or add is done or move is done, doesn't matter, okay. You, based on the need, you may do anything, but only thing is when S bit is set in the instruction, okay, format, when S is mentioned, S bit in the instruction will be set, okay, and then when the RD is given as PC, CPU automatically copies not only the PC value, okay, let me, okay, there's too many things are there. So in the abort mode you have 2 things to be copied, okay. R13 you forget it, that may not needed now. R14, which is a link register, which is holding the return value of, okay, and then SPSR, which is having the original value of the CPSR, where when the abort happened. This is the user mode registers and CPSR is here, okay, and assume that from R0 to R15, okay, PC. Now these two have to be loaded with a new value. SPSR should come here, and R14 after subtracting minus 4, okay, should come here. Plus, please note these two should happen together. These two should happen together. Why? Assume that it is not happening together. Suppose this happens first. What will happen? Originally, it was having the CPSR value before the prefetch abort happened. Originally, the mode bit was user mode. Okay, correct. The 5 bits were referring to user mode. So since we need to bring back the user mode context the same as how it was prior to the abort. We are trying to get both the CPSR to be initialized with the SPSR, because SPSR where that value was loaded, right, stored by the processor before the abort was handled. So if we move this into the CPSR, what happens? It becomes user mode, correct? So the ARM processor enters the user mode as soon as you copy this value into CPSR. Now once CPSR is having this value, this bank register, the abort bank registers won't be visible because it has become user mode. So you can't access the R14 of abort mode to get the PC. Okay, you may wonder, okay, why are you doing this? Let us do this first. But once we do this, the execution will start and the control is now no longer with the handler. So the PC is loaded, it will start fetching the new instruction from this location, and so it will be, there is no instruction to say now you have to copy the CPSR also. Okay, so you cannot, the processor cannot load the PC and SPSR separately. It has to be done together while executing one instruction. Which instruction? It could be any instruction where we are saying RD is a PC. Okay, that is what ARM has designed such a way that when S bit is set, okay, and RD happens to be a PC, this processor is not expected to only copy PC, it is expected to copy the current mode, whatever mode it is in. It could be abort mode, or it could be a supervisor mode, or it could be undefined mode, or SWA, anything. Whichever mode, the privileged mode the processor is, okay, because each one of them are having SPSR in each of them. So whenever PC is modified with S bit set, the processor automatically copies the SPSR value into CPSR. So what happens is both PC and CPSR get loaded together. So please remember, this is a very important concept which will be done in all the modes wherever the modes are modified from one to the other. Okay, when you are coming back to the privilege mode to user mode or system mode or whatever mode you are transferring, when mode changes happen, the CPSR has to be modified and that has to be restored from SPSR. So exception handling or interrupt handling will be following this always. Okay, I will be referring to this particular thing again in the other handlers also. So this should be the last instruction executed by the handler. Once this is done, it comes back to the original mode it was in. Okay, please remember, it need not be user mode. The prefetch abort could happen from any mode. So once the prefetch abort handler is handled, it comes back to the original mode it was in by executing this instruction. Okay, it's a very important concept. If you don't understand, please run this particular talk and try to get the concept behind this. Okay, this is very crucial and this is going to be followed in other places also in exceptions, interrupts. So I won't be explaining this every time. So copying both is a must. So S bit is set and RD is, when RD is R15 and S bit happens to be set, the processor automatically copies PC as well as CPSR from SPSR. Okay, so that is what happens. I'm sorry. So CPSR is restored and then mode is also changed. Okay, so this is the reason why CPSR from SPSR is done and PC is loaded from R14, because once CPSR is restored, the mode will change from abort, okay, making the abort mode registers inaccessible. Change it from abort mode. So I am not saying that whether it change it to user mode or system mode, whatever mode, but abort mode to some other mode it changes. Because of that, the abort bank register of the abort mode will not be accessible once the mode changes in the CPSR. That is why both SPSR should be accessed as well as R14 should be accessed together. So that how will you inform the processor? By writing an instruction like this. Please remember, in the instruction, the handler, the abort handler, you cannot write sub PC R14 abort. If you write, no harm. What will happen is the compiler or assembler will not give you any warning or error, but what will happen is your program will not be correct, because it will not come back to the old, previous state. CPSR will not be restored from the SPSR. So you will lose the old concept. It will continue to be in the abort mode. Though it will come back to the code what was running earlier, but the mode will not change. So please remember, code it may be accessing what user was accessing, user mode was accessing, but mode is not same, means the bank registers will be different what the program sees. So it will be totally erroneous whatever happens after that. So you have to be very careful when you are writing handlers. Okay. Now I have a question. Take 2 minutes, because I have already explained this, so you should be able to get the answer quickly. Okay, welcome back. So all of you must be sure about the answer. Yes, the option is C. I explained you earlier also that if a particular code is not to be executed, the system developer would have made sure that maybe whatever is needed, I have a memory, and beyond this I am not bothered about having a memory. But prefetch, what it does, it goes beyond the memory and tries to access something. So you might encounter the abort because the memory limit is exceeded, not because your code has gone out of control, it's because of the processor trying to do a prefetch. Okay, that is why ARM processor designers are well thought of about this kind of scenarios. So they are giving that abort only when the situation happens that that instruction has to be executed. That means that instruction is needed for the processor to execute. Then abort is raised. If it is just due to prefetch, but actually the program is not using that particular anything beyond that memory limit, then there is no need to raise a abort. So this is the reason for delaying the prefetch abort till it reaches the execute stage. Very good. Now data abort is little more complex. Okay, pay attention. I hope prefetch abort you are now an expert. Let us explain. Now let us see these two. If you understand, I think the most complex part of the ARM core is taken care of. Okay, and then rest of it is very simple, because abort handling is the most complex part of any processor, and I am trying to explain as much as possible so that you understand this fully. Okay, when a data abort occurs, the action depends on the instruction type. Okay, in the previous session I told you what are the instruction could cause data abort. Okay, please remember there are few instructions. Anyway, I will be covering one after the other now, and we'll see what are LDR and STR. They are load register and store register instructions. If okay, now take an example. This is the instruction. Okay, I hope by looking at this you should be able to understand what it means. Let me explain. Assume R1 is having a value maybe 100. R2 is having a value 200. Okay, now let us put this is the memory. Okay, now what are we trying to do here? R2, whatever is there in R2 has to be added with 4. Okay, and in that place, in that location, whatever is the content has to be copied into R1. Now I said R2 is having 200. It is added with 4. So 204 is the location in the memory which is to be accessed. Okay, assume it is having a value 2. Okay, now this needs to be copied into R1. That means it should be overwritten with the value 2. Okay, and then write back is there. Okay, what does it mean? This R2 should be incremented to 204 now, because that access has happened. So R2 will become like this, R1 will become like this. Hope you understand this instruction. Once you put a write back, that means this computed offset value is written back into R2. Okay, and it is accessed first and then modified because it is inside the square bracket. So that value, new value is accessed, and then R2 is written with the new value. So R2 plus R4 is 04 is done and it is accessed, and then now R2 becomes 204. I am saying that there is a data abort. What does it mean? The 204 is not in the memory. That means it's not only one location missing from the memory. It is assumed that up to 200 the memory was there, physical memory was there, and then from 204 to higher addresses, maybe that page is exactly the your page. See, remember that page boundary can happen at any word boundaries. Okay, so at 204 when it was trying to access, that memory is not there in the memory. In the page is not in the memory, so data abort has happened. Now what needs to be done? This particular memory has to be brought in, and the same instruction has to be executed again. So when this needs to be done, again you have to bring back the pipeline. When this LDR is executed, okay, code memory. See, there's nothing to do with the memory. This data memory. This is data memory. Okay, the 204 or 200, whatever is there in data memory. The code may be in some other location which is some 1000. Okay, our favorite address, and this LDR was there. Okay, and then 1004 and 1008. There are some other instructions. Okay, add and then sub. So add is here. Okay, and sub is here. Those instructions are here. Now when this LDR is executed, because the data abort happens only when execution happens. Please remember, prefetch abort happens when the code is fetched from the memory, because that time itself it will be known, but the reaction or handling that abort is deferred till the execute stage, but actual abort happens during the prefetch stage, whereas any data abort happens during the execute stage, because data is from memory is accessed only during the execution, not during the prefetch, not or not during the decode. So now when it is executed, this abort has happened, and what happens, similar to what I mentioned, in the abort mode there are two registers, right? As I told you, R14, R13. Okay, so R13 we don't bother right now. R14 anyway is required, but we are only looking at R14. So this R14 is loaded with PC. Which PC? Which address would have been loaded now? Assume that when this LDR was executed, which is at a location. Okay, LDR is at 1000. I said, right? LDR is at 1000, and then this abort has happened. What was the PC value will be? It will be 1008. You agree? Because already this is success, plus 4 is success, plus 8 is being accessed, and then the abort has happened. So R14 will be loaded with the 1008. Okay. Now it has to be rerun. This same instruction LDR has to be rerun, means you have to bring back not this 1008,000. You have to get back to the PC. That is a separate. Then SPSR is there. That is a separate thing. Apart from that, write back is also there. So the R2 register should also be preserved. Okay, it should not be written with +4. Otherwise, when this same LDR instruction is executed, it will start executing not from 204. It will start accessing 208, because after that offset is added. So R2 should be, old value should be there. Okay, so what I am saying is, when write back base register is specified, the instruction then abort handler must be aware of this. Why write back? It should be aware. The handler should be aware of the write back, because whether this base register is modified or not during the execution of this instruction should be aware. Okay. So in case of load instruction, the ARM process prevents overwriting of the destination register. So when you are, in case if you are loading into some register, you have to the processor has to make sure that base register is not overwritten with the value from the memory. Okay, that means this R1 should not be modified, because if you want to execute this LDR again, the R1 should be old value and R2 should also be old value to the maximum possible. Now, suppose memory corrupt data abort has happened, some wrong value would have come into the data in register, so you should not be copied into R1. That's what I'm saying. The processor will make, has to make sure that R1 is not copied and the R2 is also restored with the old value, so that when this instruction is executed again, it will run it, the same instruction will run properly without any problem. So that is what needs to be taken care of during the abort when you are running the LDR. Now let us assume swap instruction. Swap does actually two things, right? It copies, this is a destination register, okay, RD. So it copies what is in R2 and then it writes back R1, okay, into R2. So one read, this is one read, and then one write. This is the swap. So data abort, when can it happen? It can happen in either during this time or during this time. One typical example will be, can you give an example where read goes through properly but write results in an abort, and it will be difficult to correct it in the abort case also. Suppose a ROM memory is by chance is accessed for a swap, because of illegal pointer or something, some pointer corruption, you are trying to do a swap on an address which is mapped to a ROM. So reading could happen properly because not a problem with reading a location from ROM. But if you want to write into that, then there will be abort. So this cannot be recovered, but I am giving an example where the abort could happen in either read or write. So abort on read access suppresses the write access. Okay, once abort has happened, because you know that first read happens, after that write happens in a swap instruction, right? So if there is an abort in read, then the processor makes sure that there is no write cycle followed by that. It aborts, it doesn't allow this write cycle to happen. That's what it says. Suppresses the write cycle, as well as it doesn't corrupt the value in R0. It doesn't write anything into that as a result of this instruction. So it will be, abort will be handled and the same instruction will be executed again. Whereas if abort has happened during the write access, it only suppresses, so you cannot, read has already happened, okay. So write is also happened, but abort has happened during the write. Then only copying into destination register is avoided. See what I mean, this thing is the processor internally handles this, because the processor only is executing this instruction, so it can know when an abort has happened during the execution. It knows what to do with the execution. Okay, it is executing the instruction and then halfway through it is stopped. Now what all can be done, what all cannot be done, these are all well defined, because the processor, everything that processor does is all predefined. The designers would have already thought about it, and if suppose abort happens during the execution, what all it can do or what all it's not supposed to do is already predefined and put into the design. So that is why I'm saying that when the write back is there, it knows write back instruction is being executed. So processor is aware of what instruction is executing, and it is aware that during the execution of this instruction I have encountered a abort. Now these are all the design decisions taken by the process designer, that the processor will handle this in this scenario like this, so that the recovery is possible, and then running the same instruction after fixing the problem is also, correctness is assured. So to achieve this, these are all the rules put into the designer, in the design of the processor. So if suppose write access, during the write access abort has happened, it suppresses the write into the destination register. That means what? The old value of R0 is retained. That's all. Because if you remember the data path, there is a data in register, the memory content comes and then it gets written into the destination register. So this will not be done by the processor, because it knows that this execution is halfway through stopped. So processor can take action. Please understand all these things. You have to remember the context in which the abort is happening and what is the processor doing. So the whole concept and the context and the pipeline should come in your mind to understand these concepts. Okay. Now we are getting into a more complex instruction. Okay, this needs a lot more understanding. Let me explain you. What is LDM? Load multiple. Understand that. IA means what? Increment after. So what is the register? Base register is R2. Assume R2 is having a value 200. Okay. Let us try to understand what is this instruction mean, and then we will see what is the reaction done or what is the action taken by the processor when there is a data abort during this instruction. Please understand the instruction first. Okay. So what are we trying to say here? Wherever R2 is pointing at, okay, whatever address, from that address onwards, copy how many registers? R1, R2, R3, R4. 4 registers you copy. 4, okay, let me tell you 200. Okay, let me always say that, okay, this is lower address and the higher address, to make it easier to understand. Okay, sometimes I have understood, I have drawn the memory in a different direction. So 200, 204, okay, 208, 2C. Now some value is there in this memory, they all need to be copied into these registers R1 to R4. So which location will come here? This will come to R1, should come to R1. This content of this should come to R2. 208 should come to R3 and 204 should come to R4. Okay, and then R2 should be incremented after. That means what? You access this and then increment it. That's why I said originally it was having 200, means the value at this location will come to R1, then only it will be incremented. So it goes up. R2 goes up. Now after the execution is done, when suppose this is successfully done, what will be the value of R2? Please remember, I have intentionally put the base register as well as I have mentioned the same register in the register list. Okay, so originally it was having 200, and then processor takes that value. Okay, it puts it in the address register. Okay, which is connected to address bus. Okay, if it is supposed to access from 200 to 204, no problem. The lower address is 200, so that is put here, and then it will do a sequential access of 4 addresses. Okay, so keep on accessing those locations one after the other. You remember, first is non-sequential access, and then 3 sequential accesses will be done, so that you will have a sequence of memory accesses happening, and then now R2 value will be loaded with the new value which has been in the memory. Assume that there is a value 4, suppose here. Now R2 will be having a 4. Please remember, R2 is not, though it says the write back is there, okay, R2 is not incremented to 20C. Okay, if normally should have happened 20C, the new address should have come here, but because R2 is also in this list, please remember the base register and the register list can be same. That means you are using this as a base register, but you are copying a new value, the loading a register from the new value in the memory and overwriting the base register. Okay, so it is supposed to have been copied from the memory with the new value which was there in the 204. These are all good when there was no memory abort, data abort. Everything should have happened without any problem. Okay, but I am saying that there is an abort happened. Now what should the processor do? Okay, to bring back to the original state, to the maximum possible stage, so that this instruction can be executed. What I mean by maximum possible, I will explain you. Same memory, okay, 4 locations are accessed and then the registers are copied, R1 to R4 values are copied. Assume that when it was trying to write into R3, okay, let us assume that R2 is also written into, okay. If you remember, the old value was 200, right? R2 was having 200. So 200 was there, 202, 204 was there, but 208 where the abort has happened. Okay, it was not there in the memory. So this is successfully overwritten, this is also overwritten, but now R3 when it is trying to access the 208, now data abort has happened, abort. Okay, now imagine what has happened. R2, which was a base register, is already overwritten with the value which was in the memory, which is 4. If you remember, I was saying that it is having a 4, so it is overwritten. Now how will the processor can either get this value back? Because why should it get the value back? Because it has to execute this instruction again. When you have to execute this instruction, it should be back to 200, then only the original intended action can happen. But if that R2 has been already overwritten with the value in the memory, it is lost forever, isn't it? But what does the processor do? Okay, it has got a recovery mechanism. In this case, I will tell you how it recovers. Okay, assume the processor, you know that it has got to address the register where it has put the original address 200 and then said it has to be incremented for 4 times to access the memory. Now what does the processor do? Okay, when in between there is a abort, it knows the original address it started with. Okay, and then please remember the whole instruction which is to be executed is inside the processor. So if you recall the register list, okay, register list is mentioned in the instruction itself with the bits 1 to indicate that which registers are to be loaded or stored. Okay, now see, you assume data abort has happened something in between, somewhere in between. What does the processor do? It will bring back, okay, before giving a control to the abort handler. What does the processor do on its own? It knows which are the registers are to be copied from the register list. Correct? You agree? Because it has got the register, instructions inside the processor, so it knows which are the bits are 1. So it knows in this instruction whether how many registers were supposed to be copied. In our example, it is 4 registers. It knows. Okay, and then it also knows whether write back was there or not. Okay, because one of the bits here indicates that write back is enabled. And then it also knows which is the base register. It knows R2 was the base register. So, and it also has the address where it is started off with the instruction access, data access. So, from the register list, it will know how many registers are to be accessed, and it knows that whether it is a word access or a byte access, right? LDA, anyway, in LDM, it is all a word access. So, okay, so it knows it is a word access. So, you agree that it can get back this 204C, the lost value. If suppose this instruction was executed successfully, what would have been the value of R2? It knows, because it knows how many registers are to be accessed, and then it knows it has put the value in address register, so it can keep this value somewhere, okay, before the memory cycle starts. Because you remember, once the memory cycle sequential access starts, this will be incremented. So it can still build that back, because 4 would have been 4 times would have been incremented, because from there it would have it will be maintaining a counter to say how many times it has been incremented to access from the memory. So somehow it can get that the value 2.0C. So when the abort handler is control is given, R2 is put 2.0C. Okay, that means what would be the value of R2 if the instruction would have been executed fully? That value will be put in the base register. Please remember, it will overwrite, though the new value was copied from the memory, it will again restore it back to the base address, because it is going to be aborted now. So if this instruction has to be re-executed, so R2 should be having a valid value, but instead of putting a actual original value it started off with, because that was overwritten by the memory, it at least gives you a path by which the controller, the handler, can come back, overwrite the value with the original base register and then execute this instruction again. To enable that, it will load the value of base register as if the instruction has been completely executed. Okay, and then it gives the control to the abort handler. Now abort handler can also read the instruction because it knows which memory location R15, it knows which memory location the abort happened, so it can read the instruction and know how many registers were there, and then it can reconstruct this value if from 4 registers were there and it was increment after or decrement. Based on that, it will know whether +4 or -4 into 4 needs to be done, and that operation can be done, and it can recover the R2 value also. But what happens to the register R1 which is copied? It is permanently lost. So any register which has been copied from memory is lost, but it can reconstruct to the maximum extent, and then it will rerun the instruction again. This is what happens during the data abort. So hope you understood this. It needs little bit more of thinking and understanding of what is happening. So if you don't, please again read through that or hear this particular part of the talk, you will be able to reconstruct what happens. So the write back is specified, the base register is updated. So if the base register is in the transfer list, R2 is there in the transfer list, has already been overwritten with loaded data by the time that abort is indicated. I told you that abort has happened after the R2 is copied. Now the base register reverts to the original return back value as if the whole transfer had taken place. That's what I'm saying. It comes back to the original transferred, as if original transfer has happened, and then the write back value is written into, not the copied value. So once the write back value is there, the handler can reconstruct the R2 value and then rerun this again to load these values again. R1 and R2. So why is this so important? These are all is required so that after the abort, when you run this execution in the same instruction again, you will get the same effect that you would have got prior to the abort. That is the intent. So for that you need the original base address. Original base address, if you don't have, then the instruction cannot be rerun again, because it will access some other location, not the original base register. So that's why this whole thing is done this way, and then the execution starts again. So whatever the processor is doing is only enabling the handler to take care of the remaining part. So handler has to do a lot of job. It has to reconstruct the original value and put it into R2, as well as fix any page which is not there in the memory to brought back, and then rerun this. It has to compute the value which has to be which is pointing at the same address instruction which caused the abort, so that it will be executed again. So the data abort handler also has to do a lot of job, but simultaneously the processor also has to do enable for the handler to do its job. So ARM handler processor prevent all register overwriting with the loaded data after an abort is indicated. So it cannot prevent it prior to that, because as the value comes in, it is getting written to the register. So once the register is copied with the value from memory, it is gone. The previous value is gone. Only thing is, it can recover as much as possible. Suppose when the abort happened, after that it will not allow any copying to the register. Suppose up to R2 it is copied, R3 and R4 are old values. That's what the processor does. This means that the final value of the base register is always return back value if the write back is specified. This is very important. If you read this in the manual, you may not get the background of all this. So I try to explain with an example in this talk, so you will be able to appreciate what is happening and why a processor does all these things. This is very, very, very most difficult part of the architecture. If you understand this, it will be very, very easy for you to realize what is happening inside the processor. The understanding this about will give you a clarity. Now I am giving you another scenario where the list is very huge list, R1 to R15. Almost all registers from R1 to R15 are copied. From memory overwritten. R0 only is left for some reason. I have just given you the example code like this. If such an instruction is there, if there is a R15 needs to be copied, you are sure that the registers are copied from lower register to higher register. I have already told you, whenever there is a register list mentioned, the first register which is copied with the value from memory is the lower number register, okay, and then address which is successive is from the lower address, okay, lower to high address and lower register to higher address, higher register. That is what is the way copied or copying from memory also or writing into the memory also is done in the same way, so that there is a consistency between storing and restoring the values. So this actually indirectly helps also that R15 is not affected if there is a abort. See, worst case abort could happen when the last register is success. You agree? It could be the last word which is success is causing the abort. If R15 also successfully success, then there is no data abort requirement at all. But if during the R15, when you are trying to fill the R15 from memory, there is an abort, then also the R15 can be preserved. Okay, because R15 preserving is very important, because if you want to come back to the old instruction and then you want to run it again, okay, this value should be proper, otherwise you won't get this address at all, right? So this value should be preserved. So R15 is always preserved during the abort because it happens at the end of the transfer list. So after fetching the abort, the instruction can be rerun. Now this is the very now you will be able to understand this. Why is the -8? Very simple. You see, you have this load instruction which caused the abort, okay. So +8 would be the PC value. See, please remember, whenever abort happens, the current PC is stored in the R14 of the abort mode, okay. So when the return happens, you have to, the handler has to do the correction. Processor just copies the PC into the R14 and forgets it, because abort has to be handled, so it doesn't have time or anything to even look at the value of this. Only thing is, whatever PC is there is loaded. Now you have to subtract it by 8 so that the instruction which caused the abort is brought back, and you are sure that R15 is also not overwritten even if it is in the register list of load MAA. This is the worst case scenario, okay. So that means you will be able to get back the old instruction with the previous R15 value and then original base value, so that you can successfully execute this instruction after fixing the problem which caused the abort, okay. So this I have already explained. Both SPSR and PC are restored, so that both CPSR and PC gets the old value, okay. This is the most critical part of the code, so we have handled that. If the handler has copied the return address out, okay. This is another small caveat. If suppose abort is happening, repeated abort is happening. Suppose you got into abort mode, you are running the abort handler, okay. It's supposed to be careful, but abort handler, okay, itself is causing another abort. It could be a prefetch abort, it could be a data abort, okay. This scenario you should remember. When recursive abort happens, what really happens is, now one abort has happened and then you are executing that, and another abort happened. Now there is only one register which is R14. So this R14 value which is having the return address of the original abort, okay, from here the abort came, and then this has caused abort. So now this return address, okay, this address of this instruction will be copied into R14. Now what happens? The original R14 value is overwritten by the new abort return value. So to prevent it, this R14 should be copied into the stack of the abort handler. That's why the stack comes. R13 of the abort handler, okay, stack, you copy that, so that it is a very detailed thing I will be explaining you later on. Just giving you an example here, that if you are to support, okay, a re-entrant behavior, that means the same abort handler could be called again, then it has to save this R14 and SPSR value, okay. That is also required, because that also will be overwritten by another abort happening. So these two values should be copied into the stack and then restored at the appropriate time, so that original instruction can be traced back and then the control can come back, okay. So that's what I am explaining here. The restoration of the user registers and return may be, if you want to suppose OS is running and the user registers are to be restored, that also can be done, because handler will be overwriting those registers which are used by the original program. So handler has to be take care of any register it is using in its program is copied into the stack before it uses and then restore it back from the stack before coming back to the original address. Okay, that is a typical thing. So that can be done by this instruction. Okay, multiple register transfers can be done, and why this this indicates that it has to copy not only the PC value, also the SPSR value into CPSR. Okay, similar to that S and RD having this is another way of in LDMA, because you can't mention a S here, right? PC is there in the original list. This is used to indicate that when this instruction is executed, PC is modified from R14. Okay, or actually it is from stack it is taken. So it is from the stack PC value is loaded. Actually it is a R14 value which was in the stack is copied into PC, and SPSR is copied into CPSR. Okay, both should be, whenever mode change happens, this both has to happen. So that is what is done by the processor. PC will be the last item to be transferred from the memory. Okay, this is a special form of instruction which indicates that when if you are using this instruction to restore the value on return from the handler, okay, please mention this at the also as a part of the instruction. When PC is also in the list, then the processor understands that you want the SPSR also to be restored. So it will do the PC copying as well as SPSR to CPSR will be done automatically. That is what it means. Okay, similar to what I explained for the MOVES. Okay, I hope this is very clear to you guys. Now little more, we are getting into another software interrupt. This is, if you recall, I said unprogrammed aborts are this data abort and prefetch abort, which the programmer do not have any control on, whereas SWA is given by the programmer as a part of the instruction. Okay, and which can create an exception. Okay, this is also a small you need to be very careful about this when you are writing a code. Okay, let us explain, and let me explain you. This is original conditional flag. So SWI also can be SWI EQ you can put. Okay, that means if 0 flag is set, this will be executed, otherwise SWI EQ will not be executed. That's the conditional flag. Okay, let us now, there is a command field. Assume that something is written into this, but the processor doesn't use this value. Okay, it knows this all one means it is a SWA instruction, and if condition satisfies, it executes the SWA instruction. That means what? So it enters a supervisor mode. Okay, let me tell you one example. Suppose under location 100, you have put an instruction called SWA 0x11. You might have seen it in the ARM simulator that this is very often written. Now the 0x11 is stored in this location, and then the SWA instruction itself is in the address 100. Now when this happens, it goes to the interrupt vector table. Okay, whatever is the entry for the SWI, okay, that branch happens, and then it handles the SWI handler will be called. Okay, it is all very simple. Now what happens during this time? PC is copied, whatever the PC value is copied. Okay, actually PC -4, it will be copied into the R14 of the supervisor mode, and then CPSR is copied into SPSR of the supervisor mode. Please remember, whenever SWA is executed, the processor switches from whatever mode it is. Assume that it is in user mode, it switches to supervisor mode. Okay, another mode which I have shown, and then there are two registers, bank registers R14 and R13 are used for that purpose. Okay, so this saves the PC value and CPSR value into SPSR, and then it goes to that mode, supervisor mode. But this parameter field is not used by the processor internally, but it is used by the handler. So this is saved it into these values are saved, and it accesses from the fixed location 8. SVC handler is called. So far so good. Okay, the SWA record address is suitably protected. Okay, this is another side note. I told you earlier that this SWI is used for operating system calls, supervisor call. That means it is a protected call. The code which is OS only can be run. So you cannot put a malicious code into this. That means what? We cannot modify the location 0x8, which is a vector address. Okay, should not be allowed to be modified by the user program. Why? If suppose user program is allowed to touch this vector address, user can always write a branch to his or her own code, so that he can indirectly take control of the processor, because as soon as SWA is executed, it enters the supervisor mode. So supervisor is protected mode, but if you allow the vector table 8, which is actually the supervisor handler, okay, the SVC handler, if it can be modified by the user, then you are given a backdoor entry into the processor. So to allow processor, the user code to be able to control what is put here. So it should be the OS code which comes up first, should be initialize it, and nobody should touch it. So that's why I'm saying that this vector can be protected, so that user mode, we can even implement OS and protected. No, you can run the operating system code from the supervisor mode. Okay. Okay. It needs some OS background, but I hope this clarification, this explanation was clear to you. Now, how does SWI return from the handler? Okay, it is processed, now handler is executed. Now you should come back to, let me ask you one question. Should it come back to the same SWI, or should it come back to the next instruction? See, data about prefetch abort, that instruction caused the, it was not completed, so some fixing was done, pages was brought, and then the same instruction was executed in the prefetch abort and data abort case. Whereas in SWI, this is like any other instruction. So it is executed as soon as the handler is run fully. Now after this, it should come back to the next instruction, not the same instruction. Please remember. Okay, that is what is the intent. So what is done? It does this. Move as PC from R14 of the SVC mode. Please remember, this is a supervisor mode. SVC mode is supervisor mode. It has got R14 register. This R14 register has the return address to the next instruction of SWI. Okay, SWI was here. If it was 100, the 104 is the address which is stored in this, and okay, the processor takes care of initializing the return address next to the SWI instruction, similar to what it was doing for branch. If you remember branch with link, it was copying this address, the next address, into link register, right? It does the same thing because it is similar to the branch instruction, because the control has to come back to the next instruction. That is why processor takes care of giving you the address which is next to the software interrupt. So it has to come back to that by just copying that value into PC. Okay. So note that the link mechanism is not re-entrant. This, if you say, if you want to make it re-entrant, then R14 will be overwritten, similar to what I explained to you earlier. R14 and the SPSR needs to be copied into stack. If you want to make it re-entrant, please don't bother if you don't understand it now. When I talk about re-entrants and the interrupt handling, it will become clearer to you later. Okay. Only thing is, what I want you to remember that is, if R14 is used, okay, whenever SWI or any in this case SWI is encountered, R14 will be overwritten with the next instruction. So inside the handler, if you put another SWI, it will again it will overwrite the value of R14. That's what I'm trying to say. So you have to save it in stack if you want to restore it. Now, how do you process the SWI handler? How does it process the value here? Okay, this 24-bit is used to communicate some information to the processor. Not the processor, handler. Okay, handler only uses this value, what is in the instruction. Okay, so that supervisor functions can use this value which is passed by the programmer. Now this is similar to any other instruction. I leave it as an exercise to find out how 2s plus 1n is taken by SWI. I'm not going to explain that. Now I'll give you an example handler. Okay, this is a SWI handler. So prior to this, what all happened? It has stored the it has stored the location from where the SWA was created. No, SWA was called from here with some value 100, suppose. Okay, it is at the location maybe 40. Now 44 is the next location where next instruction is there. So it has stored the 4 into R14 of the supervisor mode. Okay, and then CPSR value is copied into SPSR, and then control went to 0x8, if you recall. This is a vector table address. From there it is branch to this subroutine has been called. So handler is come. This is the first instruction it encounters. Now it is executing this STMFD. That means what? In the stack, okay, full decrement. That means currently it is copy, it is pointing at this location. This is which stack pointer? R13 of the supervisor mode, SVC mode. Okay, R13 of the supervisor mode is suppose this is some 500. It is looking, it is pointing at the stack which is a full location. Okay, this is the standard. It is using this particular way of stack manipulation. That means while storing, it is decremented, which is pointing at full. That means what? It is decremented before copying any value. So it is copying what are the values. So decremented means going towards the lower address. This is will be 404FC, right? 4FC. Okay. So it is going down. Now how does it copy from the lower address to higher address? Please remember the stack will all LDM copies from lower address to higher address, the register. So let me, how many values are there? R0, 1, 2, 3, 4 values are here, and then 1 here, 1 here. So totally 6 values. So this should not be touched because it is full. So 1, 2, 3, 4, 5, 6. So after this execution, the stack would have gone down so much, and the value will be lower address. This is the lowest address, right, from 500. So R0 will be copied here, R1 will be copied here, R2 is copied here, R3 is copied, R12 is copied, and LR. What is LR? R14. Okay, which register it is? It is a bank register of SVC. Please remember, it is not the original user mode R3 or some other mode. It is a SVC mode R13. It is pointing at a stack, its own stack, and then it is pointing at a full location, so it cannot be copied where it is pointing at. And full decrement means it has to be decremented prior to storing. So the storing happens into the stack, by pointing by the SP. SP is R13, and there is a well, erase this so that you see the you see that there is a exclamation mark here. That means write back has to happen. Stack has to be advanced. So it is brought to this location, whatever the lower value is. Now what happens? It has saved this value so that this instruction, this handler can use those registers. Okay, it is saved into its own stack. And then what does it do? It copies the SPSR value. I told you that if you want the SW handler to be re-entrant, it has to save the SPSR value. Okay, as well as R14. R14 is copied here. SPSR is, you cannot access the SPSR or a CPSR directly. You are in the SVC mode now. So the processor is in SVC mode, so it copies into R0. R0 now it can be overwritten because it has been already saved. The previous value has been saved. Okay, so the handler can freely access the R0 here. Okay, so it copies that SPSR into R0 and then loads it into stack. That means it is SPSR value comes here. Okay, so effectively what happened? R14 and SPSR are the values which have been copied by the processor prior to coming into the handler. Now they are into the stack now. So now one more SWA is executed, it can freely execute because these values are saved in the stack. So it will go below and then it can come back, recover back from the handler. Okay, that is the reason why we are saving this value. Okay, now what happens? Please pay close attention to this. Okay, now it is doing a LDR R0 LR minus 4. Okay, so let me create some space for you. See, assume that originally the instruction what was executed was in some place. We have it here. Okay, 44. Okay, so LR is actually this 44 is copied into LR. You agree? Before the processor came to the abort handler. So the R14 is having value 44, which is the actual instruction next to the original instruction which caused the SWI this exception. So when you say LR minus 4, it is accessing this location, and then whatever is the content of this location, what is the content? Actually instruction itself is copied into R0. The original instruction, SWI instruction which caused this handler to be executed is copied into R0. Please remember this. It is very important, because R14 is already copied by the processor prior to executing the entering the handler. It is already copied with the return address. Okay, which happens to be the next location after the SWI. So that value is there in R14. So you can always get back the instruction which caused the handler the exception, and then it is minus LR minus 4 is done, and then it is copied into R0. Now R0 we are interested in getting that value. Okay, I told you 24 bits are used for passing as a parameter to the handler. How will it get it? It has to get it from the instruction only. So first the 8 bits are waste. It is not required by us. It is required for the processor. What the handler is interested in the remaining 24 bits of the instruction. So it masks of the lower 8 bits and then gets the value. Okay, you should know that it is invert of this will be done. So all this will be 0, and then ANDed with the value. This all will be 1. So if you AND it with the original instruction, you will get back this 24-bit value in R0. Okay, now R0 has only this 24-bit value. All these are all removed, and then it is jumping to a handler which may use R0 value, and then it can do whatever it wants using the parameter which is passed, and then it comes back here, and then it has to first copy this SPSR from there to R0. Okay, it can copy to anything, but R0 is a register which can be used by the handler, and then it is copied into SPSR. Why SPSR? Because you have in the SPSR you copied, so you are restoring the SPSR value and then executing this instruction, which will, apart from copying the PC from the R14. See, now originally R14 was pushed and then it is read as PC here. Okay, R0 to R3 and R12 and PC. This value what is there is loaded into the PC of the user mode. Okay, or whichever mode it came from, and then when you have this caret mark, then it copies the SPSR also into the CPSR. So processor comes back to the original state after this. I hope this is very clear to you. Please go through this part of the presentation again if you have any trouble in understanding this. Okay, so and then there are some more special instruction. This you know, just R15 means it will be copying R15 into from the stack it will copy into R15. Okay, only one register. If it is there, when it is copying the value from the stack, it also copies SPSR. I have told you 100 times this, SPSR also into CPSR. Okay, that is the indication. Okay, and then what does this mean? There is no R15 here, but R14 is there. In case when you have such an instruction, it actually copies the registers of the user mode. Okay, so in a supervisor mode, you have your own bank registers which are there, R13, R14 of supervisor mode. When in the supervisor mode this is executed, actually it is used by the operating system. It wants to save some user registers, then it has to get the original R13 and R14 of the user registers, not the bank registers. So to enable that kind of a saving, they have ARM designers have enabled even with R14. If you give this, it will save the user registers rather than the bank registers. Okay, it is just an information in case OS what does it do. Okay, In the privilege mode only you can use it, not in the user mode. You are already in the user mode, there is no special need. But in user mode, if you want to refer to the user mode register, the R13 or R14 of user mode register and not the bank register, it is not only R13 or R14. Suppose in FAQ, okay, you are in FAQ mode and you are executing this instruction. What does it mean? From R8, okay, if I remember correctly, R8 to R40 or bank registers in FAQ. So it will access, instead of bank register, it will access the user mode registers and then save it in the stack. Okay, so and it will save it in the FAQ stack, whichever mode it is. This will be the mode from where this is executed, and this is from the user mode registers. Okay, R13 will be the bank register, and R0 to R14. Here also R13 is there. That will be user mode register. Please pay attention to this. Minute. You have the base as well as the register list are common. Okay, and it is getting overwritten also. Okay, in this case it is not overwritten, but sometimes you can have a exclamation mark where the base register and the register list are same. But in this case it will not be the user mode. This will be the privileged mode register. Okay, so we have come to an end of the class, and okay, this is the last slide of undefined instruction. What I mean by undefined instruction means there are 32-bit wide instructions, right? You know that ARM instructions are 32-bit wide. So 2 power 32 instructions are possible in literally, okay, all zeros to all ones. How many could be there? 2 power 32 instructions. But do you think ARM has that many instructions? No, isn't it? If it had that many instructions, all of us would have found it very difficult to remember all of them. Okay, so luckily that many instructions are not there. Even if that are there, the processor needs to handle all of them. It's impossible. So there are so many holes in the instruction. Okay, it is not that all the formats, all the combinations of the bits are used by the processor to indicate the instruction. That means the part of the instruction which are not used by the ARM can be used for extending the instruction of ARM using coprocessors, or it could be like using an undefined exception. So not all instruction words are valid. So if any of the invalid combinations of instructions are encountered, what happens is, when suppose PC is accessing this and then it encounters that this instruction cannot be decoded properly because it is not a valid instruction. Okay, during decode only it will realize, okay, this instruction is not following any pattern which is supposed to be done by the required by the processor. So it is not an ARM instruction. So what does it do? It still passes this to the execute stage, and during the execute stage it calls the undefined interrupt exception. So you remember there is an undefined mode also is there, and there is a separate vector table entry is there which will be called, and then same R13 R14. Okay, sorry for ordering it wrongly. So R14 is where after the undefined instruction where it is supposed to come back, return address is there, and then stack is there. So the handler of the undefined instruction can now say do something specific to the processor or a system. So you can expand or extend the instruction set by using this exception. That's what I'm saying. So instruction operation need not be implemented in software. Then a processor attempts to execute it in an undefined exception. Okay. Okay. If you want to implement it in software, you can do an undefined exception, and then handler will do the job. It could be like accessing a port or accessing memory or doing some mathematical computation or whatever you want. So you can actually give a pattern in the code which is not one of the ARM instruction, and then that takes to the undefined instruction handler, and then the undefined instruction handler can do whatever it wants. So it's similar to SWI, but it's another mode, and then you do whatever is required for the particular combination. So it can be expanded to anything, whereas SWI will be less limited. Okay, so that's all about undefined exception. So we covered the most difficult part of the ARM architecture today. I hope you understood this. Even if you have some doubts, please listen to this carefully and then think about yourself. Okay, you need to think. You have to bring different bank of registers and then different stack and then when exactly an abort handler or a prefetch abort is happening, and then what is stored in R14 and what happens on return. You have to think internally, internalize in your brain, so that you understand the complete flow of what happens. Okay, it is easy to understand, but you have to pay a little more attention to what is happening inside the processor. Okay, even that is true with the SW also. So with this, we have come to the 15th session, end of 15th session, and I enjoyed sharing the information with you. I hope you also enjoyed it. Let us meet in the next session. Have a nice day. Bye bye.